Welcome back, you guys. In this video, we're going to be looking at this idea of linear momentum. First, let's define what that is. Definition, T-I-O-N, definition of momentum. Symbol P, lowercase p, is used for representing momentum. And our textbook is going to use the arrow notation to signify that momentum is a vector quantity, so it has both magnitude and direction. And the simple definition is that it is mass of an object times the velocity of the object. Velocity is also a vector quantity. You'll see me sort of skip the arrows most of the time. Just keep in mind, you simply have to remember that momentum is a vector quantity. It's actually quite important to remember that the direction matters, and also the velocity, obviously. Now we have some units of measure. Our SI units of momentum are simply going to be kilogram meters per second. And there is no nice, slick combination for those. You simply say kilogram meters per second. Now, also, most of the time you will not hear me say linear momentum. Most of the time I'll simply mention the momentum. But it is nice to realize linear momentum is the thing we're discussing. Momentum of an object or a system of objects moving in a straight line. And the reason for that is there's this idea of the momentum of a rotating object. We would call that angular momentum. That also is very important to us. When we get to rotation, we're going to explore those ideas. For now, this is all going to be linear. Our examples and our situations will be objects moving in a linear fashion. So I will simply say momentum most of the time, and just be thinking linear momentum unless otherwise specified later on. Within this chapter, in chapter 9, it will all be linear. Now, I mentioned momentum is a vector. Super important to keep this fresh. Always be thinking about the direction of momentum. Always, always, always. Quite important. To illustrate this, let's check out an example. And so the example is going to show us, how to calculate momentum, but also how this applies to a real situation. In this example, we are going to look at something real simple. It might just be, draw this. I don't know, maybe a beanbag. Okay, we're going to have a beanbag and a super bouncy ball, and we're going to drop them both in the same height. And in this situation, since we're dropping them from the same height, just before impacting with the ground, they will each have the same velocity. We're going to be ignoring the influence of air resistance in this situation. We also are going to say that the masses are equal. So the mass of the object 1, which is the beanbag, is going to equal the mass of object 2, which will be our super bouncy ball. Oh, by the way, we're taking the super bouncy ball to be sort of an ideal type of bouncy ball where as it bounces, there's no energy lost. We'll say that energy will be completely conserved here. And so you'll see what that means in a second. So we have them drop from the same height and just before impacting with the floor. So this is kind of like a before situation. They both have a speed of v, or velocity, I should say, of v. And just after impact with the floor, so here's our after situation. Well, the beanbag is just going to kind of be sitting there, flopped, not moving, done, right? But our super bouncy ball will rebound upward, and it will have a velocity v on the rebound just after leaving the ground. And again, so velocity upward just after the impact, and velocity downward just before the impact. same values. So I'm just going to call that velocity v. That's where having an ideal bouncy ball comes into play. So here's our question. Here's the question. What is the change in momentum for each object? Write this down for clarity. What is the change in momentum for each object? Question mark. Okay. Well, the idea of change in momentum, I can look at that real quick symbolically. I have momentum is lowercase p. A change in momentum, just a delta p. And coming back to this relationship, what is momentum? It's mass multiplied by the velocity of the object. As these things go through a change in momenta, the momentum of each one, then it's not their masses that are changing, it will be their velocities. We can clearly see that. So we're going to be able to equate this to a mass multiplied by a change in velocity. All right, so that's where we're going to go with this in our calculation. Let's look at the beanbag first. And we can see that the momentum of the beanbag initially is equal to its mass times its initial velocity. That's fine. But we have to look at our situation because of the vector nature of things. The traditional coordinate system is going to have up being the positive direction, which means this initial velocity of the beanbag is a negative value. Same thing for the super bouncy ball. So we know that this initial velocity is negative, so what we have is the initial momentum of the beanbag is negative mv. All right, well, what about the final momentum? Final momentum is mass times its velocity after impact. Its velocity after impact is 0. It's stopped. So there is no momentum. No final momentum, I should say. So therefore, if we're going to be asked what is the change in momentum, well, the change in something is final minus initial. Final minus initial momentum. And in this case, that's going to be our final is 0 minus our initial. Our initial is negative mv. Negative mv. So the change in momentum for the beanbag is equivalent to a positive mv. And this is worth just letting it sink in for a second, right? Think about this for a moment. It had a downward momentum at first, and then it had no momentum. So the change had to be a positive amount, and positive would be up. Much like we had examined velocity and a change in velocity, which equates to an acceleration if we incorporate the time component. Then if we stop the object, then the acceleration has to be in the opposite direction of its motion. Well, here, the change in momentum is in the opposite direction of its original momentum because we had a decrease, specifically a complete elimination of momentum. It had downward and then it had 0. Okay, well, that is the beanbag. Now, there's a change in momentum with the beanbag. How about the bouncy ball? So we're going to go through the same process. We have an initial momentum of, well, it was identical to the initial momentum of the beanbag. These two objects had the same mass, and they both had the same initial velocity, which was downward. So the initial momentum of the super bouncy ball is also negative mv, or equivalent. So that's the same as that beanbag. So how about the final final momentum of the super bouncy ball? Well, we have, after the bounce, this thing rebounds, and it rebounds upward with this positive value for velocity. So after the impact, its momentum is mass times velocity. So we're going to find the change. Change in momentum for the super bouncy ball. It's going to be final minus initial. Our final is mv, and we take away our initial. Our initial is negative mv. And what we end up with is 2mv. And this is very significant for a couple reasons. Number one, we note that momentum is a vector quantity. The direction of momentum matters. And so how much of a change was there in the beanbags? Momentum. There was a change in an amount equal to mv. It went from negative mv to 0. In the super bouncy ball, it also went from negative mv to 0 momentum, but it went beyond that, because after the impact, it went from 0 to a momentum of positive mv. So the total change was from negative mv to positive mv, and that equates to twice the amount of change. And that's what we see here. And it's also very important because if you just ask yourself, well, wait. Look, you had an amount of momentum here that was mv, happens to be downward. But if you happen to forget the vector nature, if you happen to forget and not be thinking about direction, you say, well, momentum is mv here and momentum is mv here. And you might say to yourself, well, I already got this. I already see that for the super bouncy ball, that the change in momentum is 0 because the final and the initial are the same. That is not true. Not true. And we just saw that in our calculation here. So please, always remember the direction of your momentum absolutely matters in just about every one of these calculations you're going to do. Now, beyond that, not going to have enough space there. I could make use of that. Okay, change my mind. We're going to be also discussing quite often this idea of a total momentum. And there's a couple of ways we could represent that. We could say, well, P total, or we could say sum of all momenta, really the same thing, or we could say the net momentum, right? Now, so very much like force, isn't it? Sum of forces equals the net force, sum of momenta equals the net momentum of a system. So here's the deal. What do we have to do with this? We look at the total momentum of a system. Let me specify this, of a system. Because a system can consist of multiple objects, multiple distinct things might be included in our system. If we're going to find this, then what we must do is find the vector sum. So the sum of all the momenta of individual parts is equal to what you would call the vector sum of all individual momenta. Momenta is the plural of momentum. So vector sum of all individual momenta in the system. Vector sum. Well, all that's telling us is we have to look at things happening in 2 dimensions, or possibly even 3 dimensions, but a 3-dimensional situation won't be very common for us in this course. So in 2 dimensions, what this is giving us is this, we could say P total is, well, the sum of all individual momenta, or the, here we say the sum of the momenta. You'd say the same thing: 1 plus momentum 2 plus momentum 3 plus, as far as you had to go. But the vector sum, this idea of doing this, well, any of these individual momenta might be at one direction, and the other one might be a different direction. And how do you do this? Well, you do it the same way you would do with forces. You find what you would call the vector sum. So the vector sum really is going to consist of a sum of momenta in the x direction and a sum of momenta in the y direction. And to find each of these guys, well, that's easy. You take the horizontal or x components of each of these, and you add them together to find the sum of the x, just as it says, right? Do as many as you have to. Same thing with the y. Momentum of object 1 in the y direction plus momentum of object 2 in the y direction plus as far as you had to go. Well, awesome. So where does this get us? Well, quite simply, if we say I'm going to add up all the x components of individual momenta, and I get some sum in the x direction. And I'm going to add up all the y components of individual momenta, and I get a sum of the y components. And so I'm looking for what you would call a resultant, or I'm looking for the total, right? Well, the total, or the net effect, there's that word again. So this is also equivalent to saying net momentum. The net effect is just like combining these two vectors. So here would be your net momentum. Here is your sum of momenta in the x direction. Here's your sum of momenta in the y direction. So how do you find this guy? Well, it looks just like the hypotenuse of a right triangle, no? So net momentum. And how would you find that? That's just Pythagorean theorem. So the total, or the net momentum. And with the Pythagorean theorem, if I know the two sides, then I simply have this sort of relationship where I say the sum of the x components squared plus the sum of the y components squared, and I will take the square root of that sum, and I get my answer. Just like we have done with forces and other vectors many times. And there's also going to be some angle here, some measurement of direction that I will have to know. I will have to be able to talk about that. So I'm just going to call it angle theta. And how would I find theta? Well, just like any other situation with vectors, theta is, if I know the two sides, I'm going to use inverse tangent function. And I'm going to say, well, sum of all the vectors in the y direction divided by sum of all vectors in the x direction. And that's going to get me theta. Now, of course, I didn't have to use inverse tangent because I already knew the hypotenuse, and you choose your route, but you get the idea. So for more, for some more exposure to this, and to see how you would apply this, if you need to, take a look at example 9-1 on page 256 for how this idea would be applied. You would have sum of components, so that gives you the x and y components of a total, and you find the angle, which is giving you the direction. That way you're getting both the magnitude and the direction of that vector. Very important. Now there's more, though, that I want to look at. In the next video, we're going to start checking out how momentum is related to Newton's second law and this idea of what's called impulse. Thanks for watching. I will catch you next time.